Okay, a group of hens lays 35 eggs in a single day, of which there are, oh, bad grammar, of which, that should be a comma, or they should say there, this of which, that needs to come out. There are four, there are 4 brown eggs and 31 white eggs. Okay. If 3 eggs are selected at random without replacement, what is the probability that all 3 are brown? All right, let me open up a Word file here so I can kind of type while we're looking at this. All right, so you've got 35 eggs total, and that's 4 brown, 31 white. Okay, so that's like our sample space. What we're dealing with, what we're choosing from. Okay, it says 3 are selected. Now, anytime you're doing or selecting 2 or more things, that's when you have to realize you need to use the multiplication rule. Okay, you've got to take them one at a time and multiply. Okay, so I would like set up parentheses on my paper for the 3 selections. All right, then you want to look at how are they selected. Okay, so without replacement. Without replacement means that you're not putting one back before you choose the next one. That's where we have the dependent situation. Basically, things change, right? The numbers are going to change. You have to assume you took one of like a brown one out when you're doing the next one. All right, so we want the probability of all 3 brown. Okay, let me put that here. Probability of all 3 brown. Okay, so one at a time. Probability that the first one is brown. We want to look at, well, what's the proportion of brown? There's 4 brown ones out of 35. So that's 4 out of 35. For the second one, we have to assume we took a brown one out. The numbers change. We now have 3 out of a total of 34. All right. And then for the third, to be brown as well, is 2 brown ones left out of 33. Okay, so each time you have to assume you took one out because we're drawing without replacement. So let me get my calculator. So to calculate that, just type 4 divided by 35 times 3 divided by 34 times 2 divided by 33. All right, so now that is giving us scientific notation. And I mentioned this last time, you've got to watch out for that. Remember what that means is this is 6.11 blah, blah, blah times 10 to the -4th power. All right, so what that means is that you have to move the decimal place over to the left, because this is a really small probability, 4 places. So we put the decimal place, and then we've got to fill in 3 zeros, right? To move that decimal place, 4 places to the left, we've got to fill in 3 zeros. All right, now that's to 6 decimal places. Let's see, how many did they want? How many decimal places did they want here? Did they say? Here we go. Answer to 4 decimal places unless otherwise specified. That's important. Don't use percentages or fractions unless the question specifies, as the computer will count these incorrect. Okay, that's important. So here we go. The probability that all 3 are brown to 4 decimal places is 0.0006. Yeah? So that's, yeah, that's how that one works. And you know, they're similar. There's a lot of stuff like that. Yeah, there's a good variety here. Anybody want to see another one of these? All right, so keep working on those. Let's go on now to the addition rule, which is easier, I think. The multiplication rule, you've got these situations where you're, you know, drawing with or without replacement, and you've got to be careful, take them one at a time and multiply. And then, of course, we also have that situation where we're looking at least one. Did they have one of those? Yeah, look at numbers 12, 13, and 14. Let's do this one, and then we'll go on to the addition rule. So this one says, answer using decimals to 4 decimal places again. Okay. Based on previous experiment, the probability that an incoming email is spam, an undesired message of solicitation, is 38%. If 3 emails are in my box, what is the probability that all 3 are spam? Okay, so that's where we've got to, let me move this over just a little bit. That's where we've got to take them one at a time. And now this is a situation where we have independence, right? Each particular email has a 38% chance of being spam. So we use 0.38, always change it to a decimal for each of the 3. 0.38 times 0.38 times 0.38. And I think I can type it in this way. And it'll multiply. Yep. So you can do it with times or with parentheses in these calculators, which is kind of nice. All right, so that one is, 0.0549, that would round to 0.0549. All right, none of the 3 messages are spam. All right, so for that one, you have to realize that if there's a 38% chance that they are spam, then there's a 100 minus 38% chance, a 62% chance that they are not spam. So the probability that none of them are spam, that would be not. So that would be 0.62, again, changing percent to decimal, times 0.62 times 0.62. All right, you could get the 0.62 from 1 minus 0.38 also instead of 100 minus 38, either way. All right, so there's the probability of none, 0.2383. 2383. All right, so then the probability that at least one of the 3 messages is, that should be an is anyway, at least one is, that's debatable. All right, so that is the complement of none, right? So either none of them are spam, none of them is spam, that should be an is also. Either none, not one of them is spam, or at least one of them is, either or. So they are complementary percentages, or complementary probabilities. So 1 minus 0.2383 gives us the answer to number 14, 0.7617. All right, any questions on those? So all was 38% to the 3rd power, basically. None was 62% to the 3rd power. And then at least one is 1 minus the probability of none. So that's something you want to make sure that you remember. We went over that last time, so it's in the notes from 2.2. All right, I'll go ahead and submit this quiz. It'll say, well, you didn't answer everything, and I'm going to submit it anyway. And then we'll see that I got credit for question 4 with the eggs and these last 3. But I still failed. Oh well. So I'll have to go back and do those again. All right, so let me switch over to my document camera again. And we'll talk about the addition rule. If you have your notes, you can fill them in or just write this on other paper, that works too. Alrighty. So with the addition rule, we're going to be interested in events that are what are called mutually exclusive or disjoint. That's going to be important to notice whether 2 events can happen at the same time or not. All right, so disjoint or mutually exclusive just means that they can't happen at the same time. All right, more specifically, events are called mutually exclusive if they share no common outcomes. All right, outcomes that would be, you know, both of them at the same time. We can draw some Venn diagrams so you can sort of get a visual of it in these cases. Here we have event A is randomly choosing a student who is male, and event B is randomly choosing a student who wears a watch. So we could have a rectangle representing all students, and then circles representing the male students and the watch wearing students. Watch wearers. And I drew them in such a way that there is an overlap because I bet that there is at least one male who wears a watch. Probably several. All right. Not as many as females, I think I've noticed. But so there is an overlap because these are not mutually exclusive. They are not exclusive of each other. There's an overlap. Okay, second example. Rolling a 2 on a fair die versus rolling an odd number on a fair die. All right, well, let's see. We've got a fair die. And let me make this one bigger. So rolling a 2, that's just one specific roll, right? Rolling an odd number, that's a 1, 3, or 5. That's a separate set of outcomes, right? An odd number, 1, 3, or 5. Right, so I guess 4 and 6 are out here somewhere. 1, 2, 3, 4, 5, 6. All right, there's all the outcomes. So this set, this is event A here, rolling a 2. This is event B here, rolling an odd number. Those are separate, right? So since they are separate, they are disjoint, and that's what we mean also by mutually exclusive. Okay, one more example. Event A is rolling an odd number. All right, so that's actually the set. Event B is rolling a number greater than 4. Okay, so here's the Venn diagram of rolls again, but now we want A to be an odd number. So A is going to be 1, 3, or 5. All right, so there's event A. B is rolling a number greater than 4. So greater than 4 is going to include 5. So I've got to capture that in my B circle. And here's event B, which is a number greater than 4. So 5 or 6 are the two outcomes for event B. So these have that 5 in common, right? That's an odd number and it's a number greater than 4. Right, and the two that we're not talking about would be rolling a 2 or rolling a 4. Right, 4 is not greater than 4. All right, so there's all the outcomes for rolling a die. These 3 are in event A, and these 2 are in event B, and these are not mutually exclusive. Because they have that one roll, that one outcome in common. Okay, so the addition rule is for the probability of one event happening or another event happening. And when we say A or B, the probability of A or B, we always mean or both. All right, so the probability of A or B always means or both. Sometimes they'll say or both, sometimes they won't, but it's always included. Okay, so we call this the inclusive or. In math, that's always what the word or means. If it doesn't, they'll tell you. All right, so what is the probability of A or B? Well, you add them, hence the name addition rule. But if your events are not mutually exclusive, right? If there's an overlap, you have to subtract off the probability of that overlap, all right? So that's the overlap, the events in common, or the outcomes, I should say, the outcomes in common. So you have to look at what's the probability that they happen at the same time, all right? Which is really the same thing here. It's just that if you have mutually exclusive events, the probability that they happen at the same time is 0. So you subtract 0. So the addition rule is really always this. It just simplifies in the case that the events are mutually exclusive. All right, so for example, what's the probability of rolling a fair die? Well, it should say what's the probability when rolling a fair die of rolling a number that is even or less than 4. Okay, so we want the probability of even or less than 4. So using the addition rule, we'd say, well, that's the probability of even plus the probability of less than 4 minus the probability of both even and less than 4. Oops, got off my page there. Okay, so probability of even. What are the outcomes that are even? For rolling a die, I'm just going to write numbers instead of drawing them now. 2, 4, 6, right? So that's 3 outcomes out of the 6 possible outcomes, right? Less than 4, what are the outcomes less than 4? 1, 2, and 3. Again, that's 3 outcomes out of 6. Well, what are the ones that are both even and less than 4? 2. And that's 1 outcome out of 6. So we have to subtract that off. So 3 plus 3 is 6, minus 1 is 5 out of 6 is our answer. Now, you could do that by just looking at the rolls. If you think about it, we've got 1, 2, 3, 4, 5, and 6 are outcomes, right? what are the ones that are either even or less than 4 or both? Well, these are even, or these are, sorry, these are less than 4 and these are even. So 5 out of 6, boom. So sometimes you don't need the addition rule. You can just do it using the definition of probability. How many ways can that happen over the total number of possibilities? Right? There's 5 rolls that are either even, 2, 4, or 6, or less than 4, 1, 2, or 3. Right? What the addition rule does for you is it allows you to kind of split it out and then subtract off the overlap for when that's easier. And sometimes that is easier. Okay? Sometimes it's not easy to list the possible outcomes. So this gives us a kind of a shortcut. All right, any questions so far? Trying to keep my chat open so I can see what's up. All right. Next page. It says a card is drawn from a standard deck. What is the probability that the card is a king or a queen? All right, so standard deck. Did I get out the picture of the standard deck? I put that back in my notebook. If you don't, if you aren't familiar with a standard deck of cards, it's probably a good idea to memorize this graphic or go to the dollar store and grab a deck of cards and check it out. Here's a deck of cards. All right, so 52 cards total. We've got 4 each of aces, 2s, 3s, 4, 5, 6, 7, 8, 9, 10s, jacks, queens, and kings. We've got 13 clubs, 13 spades, 13 hearts, and 13 diamonds. All right, so in particular, we're looking at kings and queens. There's 4 of each. So the probability of a king is 4 out of 52. Probability of a queen is 4 out of 52. So we add those together. And these are separate, right? There's no card that has a 2 and a 3 on it, right? So these are mutually exclusive. So all we have to do is add. Which hopefully makes sense because there are 8 distinct cards, right, out of the 52 that are kings and queens. And then you can reduce or get a decimal, or typically, decimal. That's how you done that for the other time we did. 3 out of 52, 0.1538 out of 15%. That here. 5 out of 6. That's all right. What's the probability of choosing a king or a spade? Well, there's 4 kings, so 4 out of 52 is the probability. How many spades are there? Well, there's 15 spades. 15 out of 52 is the probability of getting a spade. But there is a king of spades, right? So these are not mutually exclusive. So we want to subtract off the probability of getting that spade. That one card that is both a king and a spade is like the overlap of the spade row in the king column. So if you were to count how many distinct cards there are that are either a spade or a king, it would be the 13 spades plus 3 more kings, right? Which is 17 minus 1 or 16. The idea is to just not count that king twice. King out of 52, and 0.2077. Next question. Probability of getting a jack or a red card. Alright, jack, there's 4 of those. There's 52 cards. And then how many red cards? So those are the hearts and the diamonds. So there's 26 red cards out of the 52. But what? There's 2 red jacks. And again, these are all the red cards here. That's a red card, that's a red card. And those are the 2 red jacks. So we need to subtract off 2 red jacks at 62. Because those 2 jacks are counted in the 4 jacks and in the 26 red cards. We don't want to count that twice. And basically, we've got 26 red cards and 2 more jacks. 28 total cards. That's what we get here too. 30 minus 2 is 28 out of 52. 28 out of 52. 5, 3, 8, 5. Alright. Questions on your list? Card. Oh, one more. Base card or black? Let's see. Base cards are the jacks and kings. 12 of those. 12 out of 52. Base cards. Black cards. After that, 26 out of 52. In fact, I think just put one off. And then these again are not mutually exclusive, right? How many black base cards are there? There's 6 of them. Oops. Let's get one. Right up. Okay. So 12 base cards, 26 black cards, 6 that are both. 12 plus 26 is 38, minus 6 is 33. 32 out of 52, 6.54. You can use your calculator from the get-go if you want. We could go 12 out of 52 plus, I mean, we can even use 1/2 the probability of black, minus 6 out of 52. Get it that way, that would, well, the calculator knows to do those divisions before it adds the steps. The sort of operation. All right, number 3. A little bit different scenario. Now we're going to be given probabilities of percentages. This is where, sometimes you've got counts and you're looking at how many out of the total for probabilities, and sometimes you're given percentages out of 100. So in a weekend, it was found that 15% of all Charleston tourists visited the aquarium, 38% visited the battery, and 7% visited both the aquarium and the battery. What is the probability that the tourist selected at random visits either the aquarium or the battery? All right, so So this one is another or, and is a really good place where the addition rule helps out. Right? You take the probability of that they go to the aquarium, add the probability that they go to the battery, but then we subtract the probability or proportion or percentage that they went to both. Because that percent that went to both is included in the ones that went to separately. So that 15% is the big aquarium, and 38% is the battery, and 7% is the both. Normally we would use percent as decimal, and we certainly can. It turns out when you're adding and subtracting, it doesn't turn out as right. 0.15 plus 0.38 minus 0.07 is 52. 15 plus 38 minus 7, and that just gives you the percentage. If you have 0.15 plus 0.38 minus 0.07, that just gives you the decimal. Be careful though if you're multiplying with percentages. So, I'm not going to do that. So 46% is our answer. Let me show you one diagram of this so you can kind of see what's going on. And we've got aquarium goers. And we've got battery goers. And we've got 7% here in the middle, right? So the point is that the 15% that went to the aquarium includes that 7%. So that means there's actually 8% that went to the aquarium but not the battery. Similarly, sound is picking up on. Okay, so similarly, 38% visit the battery. That 38% includes the 7% also, that did both, leaving 31% that went to the battery but not the aquarium. So if you take these percentages where it's all nice and split out into mutually exclusive categories, you can see that you've got the 8% plus the 7% plus the 31% that went to the aquarium or the battery or both, also gives you 36%. So the addition rule is a way of not having to split it all out. You just put the totals and just subtract off the overlap. All right, any questions on that? So then we have might have seen some of these already. I mentioned these a little bit last time. In fact, I wanted to make our own contingency table maybe as well. Let's do this one first. So this one has females versus males, and then opposed, for, or no opinion. And then we've got the totals for how many females and how many males. And then the totals for how many are opposed, for, had no opinion on a smoking ban. Okay, so it says one student is chosen at random. One thing that's kind of nice is when it says one is chosen, you do not need the multiplication rule. So that's good news. Okay, the multiplication rule is for when you're choosing two or more. All right, so that's just something to notice when they tell you, you know, what's going on, how many are chosen. One is chosen, it's going to be either the addition rule or just definition of probability. You don't need the multiplication rule unless you have two or more. Okay, so you're going to want to distinguish between those. All right, so what is the probability that the student is female? Okay, so again, probability is talking about a proportion, which is often a percentage, right? So these P's all go together. It's a good idea to kind of keep that in mind. What's the probability the student is female? Well, what's the proportion of females? How many females are there out of the total? There are 45 females. We don't care for this question whether they were opposed or not. We just want to know how many females there were out of the total to get that probability or proportion. 45 divided by 110. 0.4091. That rounds up to a 1 there. All right. What's the probability that the student is not opposed? Not opposed. Oh, okay. Well, that's not one of these categories. Right? We have opposed. So opposed would be 21 out of 110. 21 are opposed out of 110. So not opposed would be 1 minus that. Right? Or you could say, well, that's, you know, either for or no opinion, right? You could say, well, that's the same thing as 74 plus 15 out of 110, which is actually the addition rule for not mutually, for mutually exclusive categories, right? These categories are separate and mutually exclusive. Either way, you're gonna get the same thing, right? 74 plus 15 is 89 out of 110 is 0.8091. About an 81% chance. All right, so that's the same thing as 1 minus 21 out of 110. Okay. Or you could go, well, what's 110 minus that 21? 89, 89 out of 110. Either way. All right, so 21 are opposed, so not opposed is the rest of them. Oh, my dog's going crazy. All right, next one. What is the probability the student is male and is for the smoking ban? Right, this is an and question, but again, we don't want to use the multiplication rule for this situation. This is not an and then type of situation. This is an at the same time. So we can just use the definition of probability, which says, you know, well, how many are both male and for the smoking ban? And that's that 42 right there that are in the male row and the for column. So 42 out of the 110. Which is 0.3818. One second. Yeah. All right. What's the probability the student is female and is opposed? Okay, so female and opposed. again, at the same time. So how many are both? Look up here. And Savannah, can you hear me now? Good, good, good. Yeah, yesterday I was having some technical difficulties too, so hopefully it'll be all right. And it might be that the recording is still okay. I was looking back at the recording from yesterday, and even though we had a lot of times where it even cut all the way out and we all had to like log back in, the recording still, caught everything it needed to, which is interesting. All right, back to this problem. So female and opposed. Here we go. There's 8 of them, right, that are in the female row and in the opposed column. So 8 out of 110. 8 out of 110 is 0.0727. 27. All right, part E. What's the probability? Right, it always starts with what's the probability that? Right, that's the beginning of each of these statements. What is the probability that the student is for a smoking ban or is male? Okay, and this one's or. So this is the addition rule. We need to add. Well, how many are for the smoking ban? 74 out of 110. Make sure you always do probabilities, right? Out of the total. Or is male. There's how many that are male? 65. So we add those together. But these are not mutually exclusive, right? There's some that are both. How many are both male and for? 42. We have to subtract those off. And that's important to remember. And again, it's because the 74 that are for and the 65 that are males both include the 42 that are both. And we don't want to add those twice. I mean, we want them in there, but we don't want them in there twice. So subtracting it off takes away the duplication. So you can do these separately, or you can just do the numerators. Remember how your fractions work, right? You can go 74 plus 65 minus 42, 97 out of 110, and get 0.8818. Right? Or you could go 74 out of 110 plus 65 out of 110 minus 42 out of 110. That works also. Okay. I'm going to take a break after this. I'm getting tired. 2 more and then we're taking a break. All right, so F. What's the probability the student is opposed? Given she's female. Okay, given. That's a conditional. We talked about these last time. Conditional means given the condition that she's female. So this is going to be out of the females only. Females, if I can spell. All right, so this condition restricts your sample space, basically. If you're given that she's female, that means you're only looking at the females. You're only looking at that row. Okay, so it's like out of the females. So probability of being opposed, there's 8 females that were opposed out of the 45 females, okay? So again, this conditional means you restrict yourself just to that given condition. So restrict to the given condition, which is going to be for these tables is going to be a row or a column. Okay, so opposed out of the females, 8 out of 45. You might remember the notation here is the probability of opposed with that vertical bar for given female. So it's kind of like if you think of that vertical bar as a fraction bar out of the females, right? There's 45 females and then 8 of them are opposed, kind of like a fraction. Anyway, 8 out of 50, 45, 8 out of 45. 0.177 repeating, which rounds to 0.1778. One more before we take a break. What's the probability the student is female, given that they are opposed to a smoking ban? Okay, so this is the other way around, which is difference. Female, given they are opposed. So this is out of the opposed people. All right, so here we're restricted to the column of opposed people. And we want to know what's the probability or proportion of females. So that's going to be 8 out of 21. You might notice that it's, in both cases, it was 8 on top. The opposed females go on the top. Probability of being opposed given females is out of the females, whereas probability of female being opposed is out of the opposed. So 8 out of 21. 0.38095. That 5 kicks that 9 up to a 10. So that's going to be 0.3810. All right, so we're going to take a break here. Any questions before we do so? Let's see, it is 12:48. Let's start back up at 1 o'clock. And I will see you then. Okay, it's 1 o'clock. Okay, it's 12:59. Close enough. All right, so there's another page of contingency probabilities. But I think for the sake of time, I am not going to go through that. I'm going to start with counting principles. What I'll do is maybe do that next time as part of review. So we'll do that later. What I'd like to do is go ahead and start with section 2.4 on counting, which is a different animal. The idea is that to calculate probabilities, we have to know how many ways things can happen. And in some situations, there are a lot of ways things can happen. And so we have these kind of tricks for calculating these things. So, page 50 in your worksheet. Talks first about what's called the fundamental counting principle. And all of the counting rules are kind of based on this one. Let me make sure I can see the chat in case anybody has questions. It looks like I lost everybody. Yep. Nope, you're there. It was funny yesterday things, somebody keeps, turn that down. Yesterday the Zoom thing kept cutting out. It would like just freeze and then stop. And then we'd all have to start it back up again. Or sometimes it would start up automatically. And I need to close. That message is coming through from my daughter. I've got to see if I can get that to stop. Sorry. I have a daughter, I have two daughters. One who is just turned 20, and the other is 27. She's going to be 28 in October. She's going to have her golden birthday, 28 on the 28th. And that's exciting. All right, so back to counting principles. So we've got this fundamental counting principle. It says if there are m ways of completing one task and n ways of completing another, then there are m times n ways of completing both tasks in sequence or simultaneously. And we actually have seen this in the experiment that we looked at last time of tossing a coin 3 times. Let me pull that out and remind you how that worked. And we looked at a tree diagram that showed that there were 8 possible sequences. Let's see, where was that? That was on page 39 under classical examples. Tossing 3 coins, which is really a multi-stage experiment, and the idea that there's 2 options, heads and tails, for each coin. If you look at how many sequences we got there, we got 8 sequences, right? 1, 2, 3, 4, 5, 6, 7, 8. So there's 8 possible sequences. And I showed you how we came about that, or how you can sort of see that with the tree diagram, the idea that you branch out to the 2 options for the first coin, and then branch out from there to the 2 options for the second coin, and then branch out from there to the 2 options for the third coin. So you can kind of see that there's multiplication happening. And in fact, that 8 possible sequences comes from the fact that there are 2 choices or ways each coin can land, and you're tossing 3 coins. So 2 times 2 times 2 gives you the possible ways or sequences for those 3 tosses. So that's kind of what's going on here too. This example is flipping a coin, and of course heads and tails are the options there. And then rolling a die, where we've got the 6 rolls, which I won't draw. I'll just write. You've got your 6 rolls on your die, right? 1, 2, 3, 4, 5, 6. Right, that's what these are. Okay. So do I have a coin? I wonder if I have a coin. Little visuals are always helpful, right? I have no coins. Oh well, you know what a coin looks like. So what if you do both of these? Well, there's 2 options here, or 2 ways for that coin to land. And there's 6 options here. Options, that's quite the right word, but so how many overall? Well, multiply. That's what the fundamental counting rule says. It's this idea of multiplying, okay? M times N, multiply. So 2 times 6 gives you 12 overall options. Sequences of options, let's say. Let me show you a tree diagram here. If you toss your coin, you get your heads and your tails. If you then roll your die, 1, 2, 3, 4, 5, 6, are the options after getting a heads, or 1, 2, 3, 4, 5, 6 are your options after rolling tails. And so the total sample space now for this multi-stage experiment is heads and then 1, heads and then 2, heads and then 3, heads and then 4, heads and then 5, heads and then 6, or tails and 1, tails and 2, tails and 3, tails and 4, tails and 5, tails and 6. So sure enough, 12 overall sequences. Okay, and it's, you know, you can kind of see the multiplication happening with the tree. All right, so some more examples. Suppose you're planning a menu for a new restaurant. If your patrons have a choice of 4 different salads, 2 different soups, 8 different entrees, and 5 different desserts, how many meals are possible if the patron chooses 1 of each course? All right, so here we've got several things going on, and you could potentially draw a tree. I'm not going to try it, because you would basically branch out for the 4 salads, and then from each of those, you'd branch out for the 2 soups, and then from each of those, you'd branch out for the 8 different entrees, and then from each of those for the 5 different desserts. So you'd have this huge tree, and the question is, how many branches would that have? Well, it would be 4 times 2 times 8 times 5. What I like to do for these problems is draw actually a blank for each of the things that's going on or choices that's being made. In this case, we've got the salad choice and the soup choice and the entree choice and the dessert choice. Because sometimes you have to think about, you know, what goes in each blank, and then you can put them in each blank and then just multiply to get your answer. So it works out pretty well. So 4 times 2 times 8 times 5 is 320. So, lots of options. All right. Number 2. How many different license plates are possible if in a particular state they must contain 3 letters followed by 4 digits? If the letters can't be O, I, or Z, and the digits may not repeat. All right, so here definitely we've got a lot going on. You're gonna have to take them one at a time, figure out what's going on. So just drawing the blanks is helpful here. We've got 3 letters, 1, 2, 3, and 4 digits, 1, 2, 3, 4. Okay, so these are the letters, and they can't be O, I, or Z. All right, so you got to remember how many letters are in the alphabet. You got 26 letters total, right? But minus the 3 restrictions, right? So 23 letters are left for each of these letters. So you've got 23 options for each of those letters. All right, and then we've got digits. Okay, so the digits cannot repeat. So first of all, how many digits are there? We look at 0 through 9 as our digits. It looks like there's 9, but there's 10. Remember how that works? 0 is like the 10th digit, okay? So 0 through 9 gives 10 digits. So for that first digit, we've got all 10 that we can choose from. But then the fact that they say that they can't repeat means that once you've put a digit down, you can't use it again. So that means the number of choices or options for the next digit is 9. And then once you've put 2 digits down, we don't want this one to repeat either one of those. So what? Now there's 8 digits left to choose from. And then 7 choices for the 4th digit. All right, so this is what happens whenever there's no repetition. This idea of the numbers going down because one of them is being used at each stage, all right? And then your final answer is what you get when you multiply these all together. Okay. So this is kind of an interesting state of affairs here. So we've got 23, because they didn't say that you couldn't repeat the letters, right? They just said we can't use O, I, or Z. Yeah, so we got 23 choices for each letter. But then the digits can't repeat, so we go 10, then 9, then 8, then 7. So 6, 1, 3, 2, 1, 6, 8, oh. Lots of options, right? Well, you got to have a lot of options for license plates. It's like 61,321,680 different license plates. Some of these numbers are going to get real big, and in fact, you might even see scientific notation with a positive power of 10, right, for especially big numbers. Number 3, how many different passwords are possible if you must choose 8 characters? The first 5 are letters and are case sensitive. The next 2 are digits, and the last is a special character, one of these guys. All right, so here's a real, important example of, we have these passwords, and they always want you to have like a capital letter in there and a symbol in there, right, to help security. And that's because there's so many more options when you include capital versus lowercase, and when you include symbols. So that makes it more secure. So this is asking, well, how many are there under these conditions? So again, we've got 8 characters. So 1, 2, 3, 4, 5, 6, 7, 8. Typical length of a password, right? 8 characters. The first 5 are letters and are case sensitive. All right, 1, 2, 3, 4, 5. So these are letters. And of course, case sensitive means that lowercase is different from uppercase. So that means you've got the whole alphabet twice, right? 26 lowercase and 26 uppercase gives you a total of 52 options. Okay, and they didn't say anything about no repetition, right? They just said they're letters and are case sensitive. So we've got 52 options for each of those letters. They didn't put any restrictions on there. All right, the next 2 are digits. So remember, we've got 10 digits. That's going to be something that you want to remember. Again, is that there are 10 digits to choose from, 0 through 9, and that there are 26 letters in the alphabet. Okay, 52 if it's case sensitive. So again, it doesn't say that we can't repeat the digits. So this time we've got all 10 to choose from. And then the last digit is a special character, and they're allowing these special characters, 1, 2, 3, 4, 5, 6 options there, 6 choices for a special character. Usually there's a lot more than that, right? Usually they just say you can't use certain things. Here they're telling you which ones you can use because we need to know how many there are. All right, so multiply these all together. And we will see how many passwords there are. Actually, I should fix my whiteout. Let's do the roller things. Get it going. Let's see if that works. No, stuck. Oh well. All right, so we are multiplying 52 times itself 5 times. So one shortcut is to the 5th power. And then we've got 10 twice. And then we've got 6. Right, so you can use powers if you want. Obviously, that's the same thing as times itself 5 times and 10 times itself twice and then 6. Yeah? Yeah. So sure enough, this is a huge number. 2.28 blah, 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 blah. E11 means times 10 to the 11th power. Let's see if I can write this down. So 2.281224192 times 10 to the 11th power, which means move the decimal place 11 places to the right and fill in with zeros as necessary. All right. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So if I put in commas after every third digit from the right, what's that? 100, 1,000, million, billion, 228 billion. 122,419,200. Lots of passwords. So then what this is leading up to is, well, what's the probability that somebody guesses your password? Well, on the first try, it would just be 1 out of that, right? 1 divided by that number. You can get it with second answer is going to be, you know, something in scientific notation in the other direction, right? This would be 0.000 with 11 zeros and then a 4. So close to 0 that it's essentially impossible to guess that password. All right, so that was kind of cool. Next. Permutations and combinations. All right, there's a couple of formulas, and they are developed from the fundamental counting rule, but take into a situation where maybe there's no repetition, which is actually going to be the case here. So permutations are where you've got no repetition. You're actually talking about arranging a certain number of items. Like suppose you've got 7 books that you want to put on a shelf. If you have room for all of them, 1, 2, 3, 4, 5, 6, 7, then how many ways you can arrange them would be 7 choices for what goes first, 6 choices for what goes next, because you can't put the same book in 2 spots, right? There's no repetition. 5 for what goes next, 4, and then 3, and then 2, and then 1. So this is actually what we call 7 factorial, exclamation point. That's called factorial, which is the number of arrangements of n items. All right, here they give the factorial formula here. But this is on your calculator. Let me go with a brighter color here. So n factorial is n exclamation point. And this is on the calculator under the math button. And then the probability menu, PRB or PROB, depending on your calculator. So you will see the exclamation point, and you will see also these 2 formulas, all right? So you don't need to memorize these formulas. These formulas involve factorials. They're basically developed, you know, to, in this case, divide out some This is actually used for how many arrangements or permutations, same thing, there would be of some of the items. Like suppose you've got 7 books, but only 3 spots on the shelf. Then you've got 7 choices for the first one, but then only 6 for the next one, and 5 for the next one, and then you're done. So it's kind of like a chopped off factorial, is what I call it. So this is actually what this formula does. NPR, kind of like National Public Radio, NPR is the number of permutations or arrangements of n items, n distinct objects, when you're taking R of them. Okay, so this example here would be 7 permute 3 of them. Okay, let me show you on the calculator. So 7 factorial would be 7. Well, first I'll show you that, you could do it the long way and get your answer that way. So 7 factorial is 5040. That's how many ways you can arrange 7 books on a shelf, 7 people in a row, 7 anything. That's how many arrangements there are of 7 items. If you type the 7 and then hit your math button, and then arrow over either to the left or to the right to the probability menu. There's a random number generator that we don't need, and then there's NPR, NCR, and the factorial, the exclamation point. If you go down to factorial, it'll put it after the 7, and when you hit enter, you'll get 5040. All right, if you're only arranging some of them, you have a total of, in this case, 7 books, objects, and you want to permute, which is a fancy word for arrange, put into position 3 items, 3 of them. That is 7 P3. So you type the 7 first, the total goes first, and then you go to your math, over to your probability menu, down to NPR, and then enter, and 3. Some calculators actually visually put the 7 in for N and the 3 in for R, which is kind of cool. I've got one of those to show you. So anyway, then when you hit enter, you'll get that answer, which in this case is 210. Same thing as 7 times 6 times 5, this chopped off factorial, where there's 3 positions, but 7 total items. Okay, so a big thing here with NPR is the idea of position. Okay, you can think of that P as standing for putting in position. All right, they do indicate that this is when order is important. Okay, so putting into position, there's your P. All right, here's some examples. Sometimes when there's a distinction, you've got positions. Choosing all items from a group, definitely, yeah, because if you're not putting them into position, choosing all the items is just choosing all the items. So there's nothing going on there unless you're putting them into position. And if you can derive a strong argument for order being important from the context, basically, yeah, you just have to look at the context sometimes as to, yeah, are we putting these into position or are we just choosing a group? Okay. So some examples, picking a winner from a raffle. If you think about, that's a weird example. If you think about a lottery, let's do that instead, lottery. Where you're choosing a number, some number between 0 and 60, or maybe choosing several numbers. So choosing 5 numbers. Although in that case, order doesn't usually matter. Yeah, so you have to look at the context. Choosing 5 numbers, yeah, so lottery actually, they don't usually matter. Sorry, I can't give you an open example. I have to just give you a specific example. Say choosing 5 numbers from 60, where order matters. Would be 60, permute 5 of them. Whereas a combination is actually would be choosing 5 numbers from 60 where order doesn't matter. So sometimes it's a subtle difference. That's going to be 60, choose 5, 60, C5. Okay, so this one I would read 60, permute 5. Whereas this one, I would read 60, just choose 5. Okay, so that's the difference. Real important to look at the context and see. Sometimes it's real simple, sometimes it's not. Now, obviously, if you're arranging books on a shelf, anytime you see the word arrange or arrangement, that's a permutation. Okay, that's where you're putting into position. If they just say a group or a committee, that's going to be a combination. And again, there's a formula, but it's in your calculator as NCR. So this one would be used for committees, groups, etc. And again, don't use the formula. Go to your math button. I'm going to cross these formulas out. Go to your math button. Choose the PRB menu, and you will see it. You just have to type the big number first. Type the total first. Then type R, the smaller number. Smaller number. Okay, so an example here would be being dealt a hand of 5 cards in the game of poker. So in particular, let's look at how many 5-card hands are there. How many 5-card hands are there? And this is real important for probabilities of different hands in poker. And if you remember, I mentioned that the history of probability is based in old gambling games and people wanting to know what's the probability of winning. So in this case, there's 52 cards in a deck, and we want to choose 5 of them. All right, let me show you on this calculator. It puts it in position, makes it look real pretty. So type the big number first, the total first, 52. Right, and then You go to math. This one has a PROB menu, prob for probability. And you choose NCR when order doesn't matter. Of course, when you're looking at how many hands there are, if you've got cards, it doesn't matter what order they're in, right? You can rearrange your cards in your hand, still the same hand. So NCR, and then 5. See how it puts it in position for us? Kind of nice. So this is how many 5-card hands there are. 2,598,960. So if you're looking for probabilities of certain hands, it's always out of that. In fact, you could look at, for example, what's the probability of getting a royal flush? Probability of being dealt a royal flush. A royal flush is the 5-card hand that has the 10, the jack, the queen, the king, and the ace, all of one suit. So 10, jack, queen, king, ace, all of clubs, 10, jack, queen, king, ace, all of spades, 10, jack, queen, king, ace, all of hearts, or 10, jack, queen, king, ace, all of diamonds. So there's only 4 of them, one for each suit. So the probability of actually being dealt one of those 4 hands is 4 out of 2,598,960. It's pretty unlikely. Let's see. 4 out of 2,598,960 is scientific notation 1.539 times 10 to the negative 6. Would be, a lot of room, let me put it up here. That would be 0.000001539. Pretty unlikely, pretty close to 0. So those are high stakes winning. All right, let's look at these examples. Number 1, there are 12 members on the board of directors for Charleston General Hospital. If they must elect a president, vice president, and secretary, how many different slates of candidates are possible? All right, so one of the things you're going to be looking at when you're looking at a question is it asking for a probability or is it asking for a count? This is saying how many. So that's a count, right? They might follow it up with a probability question. But the first thing you need to do is, often look at how many ways something can happen. So this one is just asking for the count. So your answer is going to be a whole number, not a decimal or a fraction. Whereas if it's asking for a probability, like up here, that's asking for a fraction or a decimal. Or you could put it as a percent. This one's pretty close to 0%. All right. The probability is fraction, decimal, or percent. How many is a count? A whole number. All right, and that's what these counting rules are for. So if you want to know how many ways we can elect a president, vice president, and secretary, well, we've got 3 choices here. One way you could do this is just the fundamental counting rule. You could say, well, I've got these 3 positions: president, vice president, and secretary. How many choices or options do I have for each? Well, there's 12 members. Right? So I've got 12 choices for each, but once I choose one of them, there's only 11 left for the next one. and then 10 left for the next one. So this is actually the same thing as a permutation up here. This is like arranging the books, if you think about it. So this is also 12 permute or put into position 3 of them. So these permutations you can actually do 2 ways. You can do them with the fundamental counting rule or with the NPR. The combinations you have to use NCR, so be careful about that. 12 times 11 times 10 is 1320. And that should be the same thing we would get if we did 12, math, PRB, NPR, 3 positions. Yep, same thing. Okay, so we've got options there. Number 2. The same 12 number 4 wants to select ethics. Just remember that starts with C. That's NCI. Okay, because if you're choosing a committee, order doesn't matter. It's the same how you're sitting. Right, so the fact that it starts with C. Okay. So we have 12 member board, 12 that we're choosing from, and 4 that we want to choose. So that's 12. Choose 4. This is the only way to do this one. Okay? 12, PRB, NCR, 495. What times is it? Next page. 52. Number 3. How many different ways can a grandmother arrange the 7 photographs of her grandchildren on her mantle? All right, so it's a how many question. And it's a no, we don't care about grandmother. It's 7 photographs, that's important. And this word right here is important, arrange. That is a key word for permutation, NPR. Okay, so committee is a key word for NCR. Arrange is a key word for NPR, because when you're arranging, you're putting into position. All right, so 7 photographs. It doesn't really matter what they are, right? Photographs, books, pictures, it doesn't matter. All right, so we want to take the fact that there's 7 of them, and she is putting into position how many? Ooh, all of them. This is 7p7. So this is actually the same thing as 7 factorial, like we did for the books, right? When I did arranging 7 books on a shelf, same exact thing. 7 factorial, 7p7 is another way to do that. Or you could actually do it by hand, 7 times 6 times 5 times 4 times 3 times 2 times 1. So 5,040 is the answer for that as well. And to show you the 7p7 works just as well. You go 7, math, yeah, probability menu, NPR, 7, 5,040. Same thing. Number 4. A student is required to report on 5 of 11 books on a reading list. How many different selections of 5 can she make? All right, so selections. What do you think about selections? Does order matter? That's just choosing, right? That's not putting into position. So selections is typically going to be a keyword for NCI. Okay? Unless they then say that they're being put into some position. If they're just selected and that's all, that's NCI. Okay? We got 5 out of 11. The smaller number is always R. The bigger number is always N. Okay? So 11 books, choose 5 of them. This is the only way you can do this one. 11, math, probability, NCR, 5. 462 ways. Okay. Number 5. How many different ways can a television programming director schedule 5 sponsors commercials during the 5 time slots allocated to commercials during the telecast of the first quarter of a basketball game? All right, so here we want to schedule. We're scheduling things. What does that involve? Typically putting into position. You're scheduling things. So that's going to be a keyword for NPR. Right? Otherwise, how many are we scheduling? It looks like there's 5 of them. And we're putting them into 5 time slots. So that is 5 put into position, all 5 of them, which is the same thing as 5 factorial. All right. So this is one that actually can be done with the fundamental counting rule, just 5 times 4 times 3 times 2 times 1, right? You've got 5 choices for what goes first, and then 4 choices for what goes next, and then 3 choices for what goes after that, and so on, all the way down to 1. So either way you do it, 120. Right? 5, commute all 5 of them, or 5 factorial. All give 120. So those, you've got those options. All right, number 6. How many different ways? And again, notice these are all asking how many, how many, how many. So always getting whole number counts for these questions. All right, this one is how many, that's a different color, I'm trying to be creative today. How many different ways can a Spanish club consisting of 25 members elect a president, vice president, and secretary? Okay, here's where there's obviously these positions, right? In fact, I would tend to use just the fundamental counting rule for this one. I would just say, all right, we've got these 3 positions, right? We did one like this already. And we've got 25 choices for who's president. Once we choose the president, 24 choices for who's vice president. Once we've got those 2 picked out, we've got 23 left for secretary. Multiplying together. And that is the same thing as 25 permute 3. Put into position 3 of them. Okay, so either way, 25 times 24 times 23, or 25 permute 3, 13,800. Okay, number 7. U.S. Senate Appropriations Committee has 29 members. They wish to form a subcommittee by selecting 5 members of the Appropriations Committee. So again, committees, subcommittees. That is NCR. Okay, these positions up here tell you to use NPR or the fundamental accounting rule. Fundamental, what do they call it? Fundamental accounting principle, fundamental accounting rule, principle, FCP. Subcommittees and committees are NCR. And you use the total first, that's N. And how many you're choosing is R. So this is NCR, so 29, choose 5. 29, math, PRB, NCR, 518,755. Thoughts? All right, number 8 we already did. Number 8 is 5 card hands. We did that up here, right? 5 card hands from a 52 card deck. Standard deck of cards. You always got to remember that there's 52 cards. And a hand of cards, order doesn't matter. And in order doesn't matter, use NCR. You're just choosing. Right? You're not permuting, you're not putting into position. You just have 52 cards and you're choosing 5. And that came to 2,598,960. Right. Last one. In how many different ways, so it's another how many, can a person order 2 sushi rolls from a menu that contains 4 rolls to choose from? Well, I don't think you care what order. Now, the one thing that's going on here that would be different from just choosing 2, right? 4, choose 2. That would be how many ways to choose 2 different. You might notice that we always wanted different cards, different committee members. We never wanted to choose the same one twice. So this one doesn't specify that. How many ways to choose different sushi rolls? So we could do this in stages if we want to know, well, how many ways could you choose the same ones? Right? So 4, choose 2. 4, choose 2. So sometimes they're a little tricky. You got to think about them. 4, choose 2. There's 6 ways. But then how many ways can you choose 2 of the same? Well, there's 4 rows to choose from. So you could choose 2 of each kind of roll, right? So that would be 4. So the total then is 6 plus 4 or 10. Now we could actually count these. We could actually look. Let's suppose there's salmon, there's tuna, there's shrimp, and what would be another one? Ooh, they're the only ones I choose. Well, let's do a veggie one. Oh, all right. So there's 4 rolls. All right. So you could do salmon and tuna. You could do salmon and shrimp. You could do salmon and veggie. Or you could have both salmon, right? You could have tuna and shrimp, tuna and veggie, or 2 tunas. You could have shrimp and veggie, or you could have 2 shrimps, or you could have 2 veggies, right? Order doesn't matter, right? Salmon and tuna is the same thing as tuna and salmon. Salmon and shrimp is the same as shrimp and salmon, right? So that's why it's, 4 choose 2. But the 4 choose 2, those 6 are the ones that are different, right? Salmon, tuna, salmon, shrimp, salmon, veggie, tuna, shrimp, tuna, veggie, shrimp, veggie. Those are the 6 that are counted here. And then these 4 are the salmon, salmon, tuna, tuna, shrimp, shrimp, veggie, veggie. So sometimes you can fall back on just listing them all out. But when there's too many, of course, then you have to look at this. I mean, if there was 20 to choose from, 20 rolls to choose from, then you would have to say 20 choose 2 for how many ways you could choose 2 different rolls out of the 20, plus 20 for how many rolls you could choose 2 of the same, right? Because there's 20 options. So that would give you 20 choose 2, 190, plus the 20 if you wanted 2 of the same, would be 210. Right? So that's just, what if there were 20 rows to choose from? Okay. So that was a little harder, and sometimes you do have to use 2 different rules and add them together to get the answer. Those are a little harder, but most of them will just be 1 rule. You just have to figure out what rule to use.